Thank you. Actually, well, rather the first talk on this paper by Yamanoi on intersections of curves, of entire curves with higher codimensional loci in Abelian varieties. So let me maybe begin by explaining what are the main results. And I think one good way of understanding them is to relate them to the classical conjectures in the linear theory. So this point of view, actually, this is Damian that explained it to me. So, thank you. So everything is based around this optimistic Griffith conjecture that actually Antoine introduced yesterday. So maybe I will just take that version. So conjecture. You take X projective variety, right? Projective complex manifold. D, an effective divisor of that manifold. And inside X, you consider Zariski-Dense entire curve. And then it is expected that we have, well, it is optimistically expected that we have this sort of second main theorem. So the characteristic function of f with respect to the logarithmic canonical bundle should be smaller than the truncation at first order of the counting function of f with respect to d, plus mirror term. Obtained by comparing this to the characteristic function with respect to an ample line bundle on X. Okay, so this conjecture is typically attributed to Griffith, but some persons have some doubts about it. But what is interesting is that you can derive from it a consequence concerning intersections with a higher codimensional loci. So consequence, take X as above. And then say you take inside X a smooth, I will say smooth to simplify, smooth subvariety of codimension C. Say higher than 2. Then if you blow up X along Z and you apply to the blowing up this conjecture, we can derive some inequality. So let's say I call X hat the blowing up, D the exceptional divisor. So if I do that, I have the following formula for the canonical bundle. This is the pullback of the canonical bundle downstairs, plus C minus 1 D. So in particular, if I apply, I can compute K X hat plus D. This is just this pullback plus C. Now, if you apply you assume the conjecture is true for X hat and D for this pair. Then the conjecture for X hat D implies that we have the characteristic function of the pullback of kx with respect to f plus c times the characteristic function with respect to d. So maybe let me write f hat. Yes. Sorry, maybe d is not the best notation. You can call it e if you prefer. So I just wanted to call it d because in the conjecture it is called d. But I agree now. So you apply this conjecture to x hat and e, a divisor on x hat, and you deduce this inequality, that plus the proof of something small. So in particular, if, say, kx is trivial, then that term will disappear. And also, you have the first main theorem, which I recalled yesterday, which tells you that this term is always larger than that one, actually, and actually that one without the truncating function. So you can write the following. The counting function of ref f with respect to e. So by the first main theorem is smaller than the characteristic function. Let me so f hat. So let me multiply it by c. And now I assume that kx is trivial, so I have this, which is equal to that, and that turns out to be bounded by this. So this is equal to that, and I have this bound. Plus something. Okay, so C is larger than 2. Here I have the n truncated at order 1, and the same I can also bound from above this. And so you see that I get, in the end, C minus 1 times this is small. I can just write something small. But the counting function of f with respect to e, it's truncated at order 1. It's the same thing as the counting function of f with respect to z, truncated at order. And so the conjecture implies the following. On a manifold with trivial canonical bundle, the counting function of a dense entire curve, a Zariski dense entire curve with respect to a higher codimensional subset should be very small. Consequence, the new conjecture, if you want, X complex manifold with a kx trivial. Say Z, this time I will say algebraic subset, but it's not hard to say that this kind of reasoning is also true if Z is not smooth. Of higher codimension. Then we should have the following. The following bound on the counting function. Okay, and so what Cadorel does in the paper is to prove something which is very similar to this. It's a little bit weaker, but he proves such a thing for X complex torus. Abelian variety. So yeah, I think it would be very interesting to prove this similar statement for, I don't know, hypercolor or K3, but it seems, well, you will see, but the methods he used, I don't see how they could be translated to other situations. Okay, so I think it's time to state the theorem. So the main theorem of the article is as follows. Okay, so let me introduce a bit of notation. A will be an Abelian variety. Throughout the talk, I will have a Zariski dense entire curve inside A. And this time, we will make use of the Green-Griffith jet spaces. So if K is larger than 1, then I will, he defines inside the kth order. So this is the quasi-projective variety given by the kth order jet spaces above A. So it's not projectivized. And inside that, you can look at the Zariski closure of the kth lift of C. And he calls that WKF. So it's the XK of R1 stock, actually. A different version because it's here in this jet spaces, the standard jet spaces JK. So the theorem, Yamanoi's theorem, so which has 20 years now, says the following: for any epsilon positive, maybe I forgot the algebraic subset. So let Z inside that space. So it lives in the K stage of the tower. So contrary to before, Z is not in A. So this is a slightly more general. So consider an algebraic subset inside this, such that the codimension inside this WKF of Z is larger than. And then you will have to be able to formulate an inequality quite similar to that one, but a little bit weaker. So as I said, for any epsilon, one has that the counting function, so it's not, yeah, f with respect to Z is smaller than epsilon times the characteristic function of f with respect to an ample line bundle. And it is smaller, again, outside some exceptional subset, which depends on epsilon. So outside some finite length subset in R plus, you have this, and you don't have a control on that subset independently of epsilon. So that's why it's a little bit weaker than that. Yes, you're right. You're right. Thank you. Okay. Okay, and one thing you can do, remark. So have I said that, yeah, F is Zariski dense. So actually you see that since F is Zariski dense, WKF is dominant above A. So that allows you to take in this theorem Z coming from the pullback of an algebraic subset inside A. One can take Z equal to the pullback via the natural projection map of something living inside A of a high codimension. Simply because F being the residence in A, it means that WKF terminates the base manifold. So if you pull back something of codimension higher than 2 inside A, you will have something of codimension higher than 2 inside WK. Because phi k of WKF is equal to. Okay, so in particular, it implies a weak version of the thing I have introduced before. So yeah, maybe you could think that it holds for k equals. So what I'm saying is that it holds for k equal to 0. Basically, this is what it means. But Yamanoi's proof is written for k larger than 1. So I just wanted to make this more precise. Okay. So before starting the proof, so the way I will proceed is by successive generalizations. So I will first prove a baby case of this theorem and then give you successive strengthenings that will eventually give this result. But before starting the proof, maybe let me recall the lemmas in nonlinear theory that will be used. So actually, I think there are only 2 that are necessary. And if you admit these 2 lemmas, then you can have a self-contained proof, basically. Okay, so again, LA will be an abelian variety. L, an ample line bundle. Okay, sorry, maybe I wrote A here. The A I wrote there means ample. Okay, you can use the notation you prefer. And try to stick to L. An ample line bundle on A. And then, so the K-state space of A is trivial. So it always splits as A times something that I will denote as JKA, which is isomorphic to C and K, n being the dimension of the Abelian variety. So as I explained yesterday, what is typically done in the article is to compactify that space. So let's JKA bar be a compactification. And I will denote by HK a hyperplane divisor. So you can take a smooth compactification in that setting. There is no problem to do that because of this triviality. There is no problem of changing charts on the base. And the first lemma I want to claim, let me denote before that alpha k, the gate projection to this vertical fiber. And maybe also, let me put bars here and there to denote the fact that we can compactify that part and get this JKA bar, and you can project it to the vertical fiber by this map alpha k. So first lemma. Consider a Zariski-dense entire curve inside A. Then we have the tautological inequality, but the versions that I explained yesterday were for k equal to 1. but you can actually prove by induction works to prove the statement that I'm going to write. So consider the characteristic function of the projection to that vertical fiber of the lift of the curve. The lift of the curve is fk. You can project it to this vertical fiber and consider the characteristic function with respect to the divisor at infinity, with respect to h. Then the claim is that this is small, very small, outside some exceptional limits. Right, so again, this means that if you consider only the derivative part of fk, so this alpha k rho fk means that you forget the variation in A and you look only at derivatives that order higher than 1, then these derivatives have a small growth compared to the function, the variation of the function of on the base, which is encoded by this characteristic function. This is the kth order tautological inequality. Okay, and a consequence of so here I have formulated this for Abelian varieties, but another lemma that will be useful is true for any variety. So take X a complex projective say manifold. An ample line bundle on Y. And also, you can look at compactification of JK Y and take an ample line bundle on it. So here you take any compactification of JKY, so call it JKY bar, and consider an ample line bundle on it. And a version of the tautological inequality permits you to compare the characteristic function of the lift. So again, I take an entire curve inside Y. Not necessary as students, actually. And then what the tautological inequality can prove is that if you consider the characteristic function of the kth lift with respect to M, so it's not negligible before the one on the base, but it cannot be too big compared to it. It's a big O on the one on the base outside some exceptional limits. So what you can do to prove that is simply, if you want an ample line bundle on that, you can add a divisor at infinity. So take, as before, a divisor at infinity. And to obtain aim, you can take M equal to H plus a multiple of the pullback of L on the base. And now the part, so if you consider the characteristic function with respect to M, the part which is computed using H will be negligible, and that one is comparable to the characteristic function on the base. Okay, so that will be quite useful, but maybe tomorrow, not today, that's the second lemma. Okay, and I claim that with these two lemmas, you have nothing else to know about Nevanlinna theory. Everything should be self-contained, hopefully. So let me start with the baby case of Yamanoi's theorem. So the baby case is actually the case where I consider an algebraic cycle on the base rather than on the k-jet spaces. Take a Abelian variety. Z inside A of codimension higher than 2. Again, F Tarski-Dense entire curve. And then we directly have the inequality. So then for any epsilon, the counting function of F with respect to Z, truncated at order 1, is smaller outside some exceptional subset, depending on epsilon. Then epsilon times the characteristic function of F with respect to some fixed ample line number. Okay, so the proof of this result depends, well, comes from I think, a very clever lemma, which I am going to detail. And the construction of some, well, we'll see that later in the proof, but the construction of some sections, some differential equations, actually. So the lemma is as follows. Under the assumptions of the theorem, so for the time being, we exactly the same assumptions. So the lemma says that there exists a sequence of integers going to infinity as L goes to infinity, which is negligible before L, and depending on, so you have this sequence, and also you have sections. Let me say algebraic sections. So sections of what? Sections on the total space JKA of the pullback of this sample line bundle to the power NL. So here, be careful, JKA, so again, it's the product of the projective variety A and of an affine space JK index A. So if you have a section of that on that quasi-projective space, it basically means that you have vertical coordinates. So this, you can see it as a polynomial with coordinates in the coordinates on this vertical fiber, whose coefficients are sections of this ample line bundle. Here, sorry, wait, where is K? No, sorry, this is L. Yeah, thank you. So you take orders going to infinity, and on each of these spaces, you choose a well-chosen section, which has a not too high twist on the base. And these sections satisfy the following, such that for any, this property will be with respect to this entire curve. So for any T0 inside C, such that F of T0 falls inside the locus Z, then yes. L is fixed here. Yeah, it's you take any ample line bundle on A, and it will serve to give you the standard. So for any T0 in C such that F of T0 falls inside Z, then if you look at for any L at the order of vanishing at T0 of the pullback of this section SL, so this SL you can see as a Green-Griffith jet differential actually on A. Then if you look at its pullback on the curve C, well, it will vanish at order at least L plus 1. So maybe here, let me write. This is the same thing as the space of Green-Griffith jet differentials, but the order is not controlled. So this is JLL, EL, and let me put a bullet here. And you have a twist on the base, which is negligible compared to the order that you want to achieve. And it's, where is A, sorry? Page 0, yes. A, thank you, exactly. So here you don't have any control on that bullet, but it will not matter in the end. Okay, so so the goal is to produce these sections, this sequence NL. So how do you do that? So in Yamanoi's paper, it's quite technical, but I think in the end, the idea must be fairly simple, even though I couldn't quite simplify it too much, but let me try to prove the limit. Actually, it will occupy us for some time. So I will introduce the following bit of notation. So for the time being, I will fix L, and only in the end I will allow it to vary. So I will denote if X, say, is a complex manifold. So I will write X times C bracket epsilon to be the schematic product. Like C epsilon to be rigorous, where epsilon is a nilpotent element of order L. Nilpotent order. So this is an Lth thickening of X. So what happens in the case of Abelian varieties is that we have a natural morphism of schemes. Which between some thickening and JLA itself. So starting from the Lth thickening of the Lth jet space of A, you can arrive inside JLA itself in some non-trivial manner. So let me decompose that. A times JLA. And similarly here, I will write it as a M times JLA and C epsilon. So yeah, I won't be too formal about that, but let me write it that way, even though since we have non-reduced schemes, the formal way to write that would be a little bit different. So assume I start from a point A, a jet psi, and this coordinate epsilon. Then I can define inside that space. So A, I will shift it by actually some L, length L scheme depending on this psi. I will be more precise about notation later. And here I have to put some jets, but they will also depend on epsilon. So write f psi prime of epsilon until f derivative L time of epsilon, where this f psi of epsilon, I think it's what you imagine. F psi of epsilon. So it is, so psi, it's jets on A up to order L. So you can write it as psi1, psi2, psi L, where psi I can be seen as the vector tangent to A. And so psi is psi1 up to psi L. It's a kth jet tangent to A. And so you can do that. Depending on this psi, you can form a formal Taylor series depending on the parameter epsilon, which is a nilpotent element. And so you have all these derivatives which shift all the elements until in the end you arrive at the last derivative, which is just psi f. Okay, so this I think you cannot do on something else than an Abelian variety somehow, because if you I don't think it is very intrinsic the way. So the fact that you have a global authorization of the kth jet space allows you to define these formal derivatives for a jet at some point. But usually, if you change coordinates on the base, the derivatives of the jet will move in a way that forbids you to truncate them in that manner. Okay, and so with this morphism of schemes, the claim is that you can make a test for the sections SL to satisfy that condition. And so this test will be defined in terms of the pullback of this morphism of schemes to Z. So you can pull back this morphism via, so actually the restriction map. So if you restrict this jet space to Z, actually what you get is Z times the fiber. And it embeds inside the, so it gives okay, so maybe pullback is not the best term. I will rather say composition, because I'm just composing that map with this map at the source. So it gives a morphism psi Z, starting from Z times JLA times C epsilon, and arriving inside JLF. And the claim is that if a section here, if a section SL in that space, so living above JLA, vanishes when you pull it back by psi Z, then it satisfies that. So that is what I'm going to prove. So the proof I'm going to give is quite algebraic. you'll see that I think there is a more geometric way of stating it, which I have not found yet. So, lemma. Lemma 1 in that proof. So let S be a section as before. So if you want a going to fit the differential twisted up to some order M, be such that its pullback by Z is equal to 0. Then the claim is that this holds. And then, as you can imagine, the second step of the proof will be to say that we can find section vanishing like that with some M's not going too fast. So proof. So let S be as above, vanishing when you pull it back by psi Z. And let T0 here such that after T0 falls inside Z. So this f of T0 I'm going to call Z0. Okay. So I'm going to use some coordinates. So let Z be a set of coordinates from Z1 to Zn be coordinates in around Z0. And then you can derive from that coordinate Z some set of coordinates on the so for I between 1 and L, you have associated vertical coordinates on the space JL. So what does it mean that psi Z of the pullback of S by psi Z vanishes? Yes. They are, yeah, linear. Yeah, this is, okay, maybe I will not strictly use the coordinates. Yeah. So we can write the section S as a polynomial in these coordinates. And actually, yes, the fact that they are linear is quite important to state what I'm going to say. So if you write S that way, the fact that psi Z of S is equal to 0 implies that for all psi 1, psi L in Cn, so these are given by the, if you recall, the map is expressed that way, and the only difference is that psi Z starts with a Z here instead. But if putting back S by psi Z is equal to 0, it means that for any psi here, substituting this inside S gives 0. Okay, so I write that way. So strictly speaking, this gives 0 modulo TP, T to the power of P plus 1. And now I do something which is a little bit too algebraic to my taste, but I say that this is an algebraic vanishing true over a field of character, an algebraically closed field. So actually it means that this vanishing also true if you replace C by any K algebra. So formally, if you replace C by a K algebra, and you take psi1, psi L inside that, you will also have the same sort of vanishing. And so the idea now is to rewrite S composed to the kth jet of F under that form where the psi is well chosen. So we also have, so if you put back S by the kth jet of F, formally, locally, you have S of F of T, F prime of T, until Fl of T. And you want to rewrite it under that form, but if you remember correctly, so what you have to do is to find some formal psi such that the triangular equations that you have on the board identify with that. So you have to find the correct psi I for it to work. So you can do that inductively, starting from the end. What is? Ah, sorry, it's L plus 1. Thank you. Thank you. So yeah, I said you can start from the end. So let me write. So how did I write thing? Yeah. So let me write f of t as z0 plus maybe not psi, but zeta 1 t, etc. plus zeta t L, sorry, TL over L factorial plus a big O of TL plus 1. So now it means that FL of T, so this is zeta L plus say something which will be written T HL of T. Well, HL of T is a big O of 1. So let me define psi L as precisely this. Inside the formal ring with a variable t. And so I'm going to explain the previous step. So FL of t, this is zeta L minus 1 plus zeta L t plus t squared. And here say HL minus 1 of t. Again, this HL minus 1 is a big O of 1. So if you substitute now the psi L, so the zeta L is psi L minus something which is a big O of t. So here you find a big O of t squared. And so if you take that term and you add it to that one, you can define psi L minus 1 to be zeta L minus 1 plus something which will be a big O of t squared. So again, you are allowed to write it as psi L minus 1 plus t psi L. And each time you continue defining at each step some psi L minus 1, psi I as something which will depend on the previous zeta, and you will have a big O of t. So let me write it that way. Psi I will be some polynomial expression in the zeta I and t. And it will only be defined at each step, say, only up to some t L minus I plus 1. And so if you continue up to the end, you will write f of t as z0 plus psi 1t, etc., until psi L dl over L factorial. And there will be something that we cannot erase, which will turn out to be a big O of TL plus 1. But all the other terms will be written exactly that way. Okay, what do I want to erase? Maybe not that, I will leave this. And so what you get, maybe I can rewrite here, is S of V0 plus X F epsilon F psi of T plus a big O of T L plus 1. And after that, you have this derivative. So if you forget about this big O of T to the power L plus 1, the formal vanishing upstairs applied to C double bracket T, say, gives you something which vanishes at order T to the power L plus 1. And I think that doesn't change anything. And you get what you wanted. Okay, so as you can see, it's not very geometric. I'm not very satisfied by this argument. I would prefer something saying that you, on the Abelian variety, somehow the idea is that there is a canonical way of pulling back from one point to the other. So, yeah, I think it is hidden behind that, but I have not been able to obtain a geometric argument for that. But now once you have that, so I think, once you have that, it is quite easy to show that you can find sections that vanish by along this pullback. So why is that so? You have a lemma that says that if you write the diagrams as before, so the map sizes started from that space, that scheme, which you can also embed inside this thickening of the K to the F jet space of A. And you had this map, say, psi Z, and I didn't write it as psi A, but I used the notation. And therefore, inside A times J L A. And you have a further projection towards J and A. And so the claim is that the diagram here, the following diagram, is locally trivial above this final projection. So if you remember the expressions of the map psi Z, psi A, they are not especially, not, I think, obvious that they give a trivialization above the vertical fiber of the projection. But actually, the fact that they are written in sort of triangular form gives you this, gives you a trivialization. So what I mean by locally trivial is that, more precisely, they are a product. Sorry. More precisely, is locally a product with a triangular diagram that way. So Z times a thickening, health thickening of Z, and yeah, the projection to A. So let me emphasize the fact that this product is not the same as that one. There is some sort of twist involved. But that will be, I hope, clear in the proof. So I will do the proof for the right-hand side. For this diagram, show that the right, this psi A here is locally a product with this fiber. So to do that, I will just show that a fiber of this projection map to JLA identifies with a showing that you can formulate a local trivialization using that is not too hard. So fix a point inside this base, JLA. Then what I claim is that the schematic fiber of psi A, so it lives inside, again, the starting space of psi A. And so, sorry, the schematic fiber of the map psi A above this W1 WA. So it's, if you write that psi A of an element has this as the element inside JLA, then you will find that it is equal to A times, and now you have some equations. Simply identifying the element psi, the derivative of this f psi of t with the W1. So this is the equations I'm going to write. And so these equations are just what you imagine. So you have psi 1 epsilon, so depends on epsilon, psi 1 epsilon up to psi L epsilon L divided by L factorial until WL equals psi. Now this is a triangular equation, so you can invert it and write the psi L in terms of the WI. So this is I, A times, and now you can invert this triangular block and giving you, I'm not going to write the equation, maybe. Okay, I'm not so sure about my formula. But what's important is that something which depends on the Wi and epsilon. So what happens here is that inside that space, the coordinates along this JLI are fixed by the choice of Wi. So you have an isomorphism between this fiber and the space, which turns out to have coordinates given by the one on A and this epsilon. So once you fix the Wi landing inside this JLA, then the fiber above that will be A times, of course, this jet. And what I claim is that the fiber lying above this will be isomorphic to A times dA, so L thickening of A. And the coordinates on the second factor is can be obtained using the Wi. And you have the same thing for Z. You have an isomorphism between this fiber and the L thickening of Z. Hence this pluralization above this base manifold. I'm out of time, actually. So I will finish tomorrow, I think. Yeah, maybe so that you don't forget. So tomorrow, what I was doing, I will just explain to you the end of the proof the existence of the SL. So what you want to do now is to produce sections on this space, such that when you pull them back here, you obtain 0, and you want to produce sections of these powers. So you want sections of that vanish here, and the idea is that locally on JLA, you can write the expression of these sections, and you see that you want actually for them to vanish via this pullback, you need to have sections that vanish along an L thickening of Z. And if you count the dimensions, what you will obtain is that you don't need something which grows too fast for this NL to have something which vanishes at order L along some subscheme, which is, I think, very a striking fact, because typically, if you have a point inside Cn, if you want some polynomial inside Pn, if you want a section which vanishes at order L at 0, S restricted to the L thickening of 0, I will write 0 times L plus 1 if you want. Then if you count the dimension, they have typically the number of conditions you need to impose on S typically grows as L to the power n. And here you just have something which is linear in L. So the fact that you introduce that jet space here is the reason for that. That you have a pluralization above which the fibers are thickenings, but thickenings in only one direction given by this JL. And this is it's a very clever trick. It's basically the idea behind that. And once you have these sections, then it is an application of the tautological inequality to prove the theorem. So I will do that in the first minutes of my talk tomorrow. All right, thank you. So again, I'm not very satisfied by this. So it's not written in that way in the article. there is a thickening that is also produced, but this time directly inside that space. So actually what Yamanoy studies would rather be the image of this map, which I think is more difficult to study because it's not locally trivial on the base actually. But yeah, I think there is something which is happening with Abelian varieties that I still don't really understand. The fact that, yeah. Yeah, it will also be used in the tautological inequality for it. Right. Well, thank you.